Hello and welcome to the Inktober Engineering Challenge Day 2. I promised myself I was going to plan this a little better than last time, but here it is at the end of the day. I need to get home to my family, and so I'm just going to wing it again. I'm going to start, we're going to do a little more designing from the product out, and that again is the product that the machine produces, not the product that we're designing. But I'd like to talk a little bit more actually about business and the business side of it, and we talked about how do you define success for the machine, how do you define performance. I'm in the strange position of being both the client and the engineer in this hypothetical. There isn't a real client, so some of the things I mentioned yesterday I had 24 hours to think about, and I said it probably wouldn't apply in a situation like this. So I shared this both from as a business person and an engineer with a systems-oriented view from a designer. One of the things that I'd mentioned was that throughput might be important for this 3D, metal additive manufacturing system. Throughput in that sense is another way of saying you're competing on cost. That if throughput is really your cost differentiator, your differentiator among products, then again, it's another way of saying you're a low-cost provider, or you're providing a low-cost solution. More realistically, in the system that we're describing, there are systems that exist out there like this. Really what the client's client, you need to think of it once removed. There is you, then your customer, and then your customer's customer. And it's really these guys, twice removed from you. What are they paying for? More likely, they're paying for some unique capability that lets them make more money. So if we think about this as a manufacturing tool, this additive manufacturing that will let you do complex shapes, and if you can imagine they're involved in turbo machinery or something along those lines, where you can create geometry that results in a more efficient machine, lower cost or more energy produced by this machine, thanks to being able to create unique designs for the turbine blades. So that would be more realistically in a scenario like this. This is what this customer is paying this customer for, and it's your job as the engineer, as the consultant, to figure that out. Hopefully these guys know, but in any event, again, it's more likely that it's not throughput. Throughput will always be important, but in a case like this, I would think if we were to write down the requirements and what defines performance, it's going to be a large enough volume for these unique products, large volume, unique shape. Unique is not the right word, but otherwise impossible to manufacture shapes. And then there's going to be some level of accuracy of form. Again, if you might be producing something that is going to deal with fluid dynamics, and the accuracy of that may be critical. But those things are going to matter, I think, when we talk about the performance of this machine. The other kind of epiphany I had thinking about this, realistically, given this, that it's not a high throughput machine that we're designing, but a machine that provides unique capability. The palletization option that I described, that wrinkle, that unique feature, may not really matter in this scenario. But this is a hypothetical. We're going to go forward with it because I think that palletization it's an interesting precision engineering problem, so let's work it out. And the reason that it is because we have, as I mentioned, there's going to be high temperatures involved. We're going to preheat the material that's going to be, fused. And so we've got, if we have our, here's our platen that moves from machine to machine. And we want to carry along some features that locate it accurately and repeatedly, no matter which machine it's placed on. A classic scenario for that is, kinematic mount, so 3 balls and 3 V's. Might be one way to do that. Problem is that in this scenario, this is also terrible for heat transfer. And yet, so we want to heat this up to 100 to 300 C, whatever that may be. But if we're trying to do it through a kinematic mount, which by definition has only point contact, we're really facing a challenge. just going to be a problem heating it up. It's going to be a problem with temperature differentials across and what that may do to alignment. So it's just an interesting problem. So even if it isn't realistically something that this customer would care that much about, let's carry it forward for Inktober. The other thing about the moving from station 1 to station 2 that I think is interesting and doesn't get talked about a lot is interchangeability. We talk about, so again, going back to a precision mount and any kind of precision engineering, we can get into this later, another day, but repeatability is, so if you have a target and you're trying to hit something, and your results are like that, not very repeatable, not very accurate. Repeatability, if it's clustered like that, then it's what we call repeatable, but not very accurate because we're not on the bullseye. But when something is repeatable, you can usually address that some way in the build or in the calibration so that a repeatable machine can also be made accurate. So typically, you're probably already familiar with the terms and the relationship between repeatability and accuracy, and that repeatability is the lower limit of accuracy. You can't be more accurate than you're repeatable. There's another interesting topic that probably doesn't get discussed as much, and that's interchangeability. And I'll just abbreviate it for now. So interchangeability, so repeatability and accuracy generally refers to within the same machine. Interchangeability has two senses, and one of them is taking a platen from here, moving to another machine, moving it to another machine, so that you're getting combinations of errors. And interchangeability will say, well, does this work? And it's interchangeability you need to consider, the combination of those. The other form of interchangeability is, so we've got, we have a size 1 platen, but then we also want to have a size 2. Or we may have, I've designed optical systems where there are multiple fields of view, and you achieve that by swapping in one set of optics for another. So that would be the same notion for interchangeability. So you would define an interface for those optics such that whether, whatever field of view you may have in there, you can put in one set, and the overall alignment is maintained. So you could, again, you might have, so that's another sense of interchangeability, is you have multiple different assemblies that could be installed on the same machine, and you want to provide the same level of performance. And then the third one is just in terms of manufacturability. You want to build 100 optical assemblies that are more or less identical and pair them up to 100 different machines that are more or less identical, and you want to be sure that any combination of two of those will work. So that's another notion of interchangeability. So another reason, even though it may not be realistic that a client would actually pay for this kind of palletized system in this scenario, we're going to do it because it's neat for those two reasons. It's a good problem to address with the thermal and the precision alignment, and it really gets into this topic of interchangeability that I don't think gets discussed enough in precision machine design. So let's erase this. Yesterday I mentioned designing from the product outward, and the product is, in this case, is not what we are designing, but what that machine produces. And it can have different senses. It may not be a product at all in the medical device application, but so, and here it is, a genuine physical product, some complex geometry, can't otherwise be manufactured. Now tomorrow I think we'll take this one stage further and look at the product as this shape that's carried on the pallet. So this is going to have, we're going to have to design the transport, design the registration. These different things will be a challenge here. So that'll be, day 3. We'll look at the product in that sense as it's moving through that hypothetical factory. Today we're going to look at the product that is being generated by the machine. And what we want to look at are what are the considerations. Ultimately, we, as I mentioned, performance for this part. As I mentioned, there's going to be overall size, but there's going to be accuracy of form. So no deviation from actual form, from ideal form to the actual form. There's also going to be smallest feature size. And you can think of that as resolution. So, you know, just how small of a feature a clear feature can be defined there. And then we already mentioned throughput. So typically, this is more of a constraint. It's the machine must produce, you know, this much volume in this much time. And that's going to generally drive us faster, to do things faster, which will generally degrade accuracy. And therefore, resolution can also be dependent on that. So that's more of a constraint. We need to meet those accuracy and smallest feature requirements with the throughput. So this product that we're talking about designing, you know, again, designing from the product out, actually has a couple of states. We are, as I kind of described yesterday, this is probably going to be on a platen that gets lowered as it's built up. So if we were to go back in time, we have maybe just this portion of it built up on our platen, which is now below the surface of our machine. So here's our machine down here. In this state, here's our machine. And as I described, we actually fill that hole in, or that, actually the shape of that will be something to determine, but we fill that in with powder of some kind. And then there is this whole time heat going in to the platen, so that we warm this up to, you know, TP for T, like I called it T platen yesterday, call it T preheat. So we get what we really want to heat up is this particulate up here. But we have the opportunity, and the way we can heat it is through here. So the more we build this, the farther that heat has to travel. So there's probably going to be some limit to how tall of an object that we can make. And then the last step is we have the lasers up here drawing the pattern, doing the final melting of the fluid and allowing it to fuse into the profile shape there. And typically there is, again, some type of flow. You know, some type of laminar flow, argon or something across there to evacuate the fumes. Now this is building a layer, and then there's another state before that where we have, before we actually start heat treating it, where we have our hole. As I think about it, it's probably not going to end up as circular, but we will have a pile of material over here, particulate or wherever it comes from, and then we're going to have to level that across precisely. So we'll have something that drags that powder across to give us a nice level. We probably need to control that. So there's probably some requirement on T here. So that this is another step. So at this point, the product is a powder. At this point, the product is being solidified, and we are building up the eventual end product, which is a complete system. So we really need to consider these three states, how each of these stages affects the accuracy, and what we'll do is we'll start cataloging the sources of error or the problems that we expect to encounter. So on this one, clearly we're going to have, you can imagine that if the thickness of that layer of powder was too high, you may not get too good fusing. The other challenge would be if you had spots. If it was somehow, probably wouldn't be a local spot like that, but you could imagine a scenario where your coverage is not good. So part of the platen is not covered. So we need to think about thickness of layer. We're going to need to ensure complete coverage. In terms of throughput, do we need to wait for that to cool down a certain point? I would think not. But we're going to have some kind of mechanism, we'll call it the spreader mechanism, that will be responsible for ensuring those. There's also going to be, the spreader mechanism. Does it need to be variable height? That's a good question. Variable? Does it need to be variable? Another question in my mind, is it material dependent? Are the settings, kind of goes into the variable height, but so material dependent would be the thickness. Also, I can imagine the speed. So how quickly you spread it back and forth. We might need some control on that. Maybe some of these particulates are clumpier or just simply larger in diameter. So these are some of the things that we need to figure out and discuss with the customer. Are these going to matter? Do we need to handle these things? So the thickness of the layer, completeness of the coverage, and then I think some of the variables are going to be the thickness, the speed with which we spread, maybe even angle here. I can call it angle of attack. So maybe our spreader, can go from vertical to there. So do we need to be able to control that angle? Does it need to be automatic, one-time setup? So just as a general, so now we've got, I'm going to put spreader. Just as a general system. There's going to be much more to that in terms of recovering the powder, getting the powder sourced, things like that. But I think from a effect on the quality of the product, I think it's going to come down to thickness and coverage. So that spreader is going to be responsible for that. This is getting messy, I realize. So moving on to the central segment where we're actually processing a layer. So we get into, let's start talking about accuracy of form. So as we've described it, our notional system, and this may change, has two mirrors, and there's a laser source. So with these two mirrors that we can pivot, we can essentially create a raster image here. So this controls, that arrangement controls the XY pattern and the accuracy. So we need to be concerned about, well, just as we get into the second step, accuracy of form, we're going to actually break that into two pieces. One is the XY, which is the in plane, might be another way to think of it. At least one source is up here, maybe not the only source. And then the accuracy in the Z, as well as, this is more resolution, which in this case affects your Z accuracy as well, will be controlled by just how precisely we can lower that. So Z accuracy, or Z resolution and accuracy. There's going to be a lower limit, as well as we're going to have some machine errors I have one that I just thought of. Okay, so but that's going to have a role there. This resolution may not be strictly dependent on the actuator that we have here. In fact, the actuator, you can design something that's going to be, very, you can go into microns positioning if you want to. I do think that the thickness of here is going to be another key, so that this is also going to affect the spreader, and more just the material properties themselves are going to also affect the Z resolution. Right? So we have a large particle, there's going to be, or a clumpy particle, there will be a limit on what our Z resolution is, much more likely to be based on that than on the platen here. Now, as we start to think about, let's keep all this stuff in mind. No, I'll save that. Another error that I would like to mention. So our vertical motion is actually likely to be very precise. But, so if we have our product again, which is brown, now I'm going to do it in side view. Here's our product, and it's riding on a platen of some kind. It's going through. Here's our wall of our chamber. And here's our platen first of all, and then we're going to have a heater here, moving on our Z-axis. Okay, so this is moving down. Yeah, as we've established, that the actual, we can put encoders on this, we can measure that very accurately. But another source for the error for delta Z would be differential thermal expansion, or just expansion in general. So if we are tracking and measuring with an encoder the motion here, if we measure very precisely the translation at some point, let's say it's a delicate instrument, we want to move it away from the heat, so we have a linear encoder down at this point. So linear encoder. Well, we have, what is potentially problematic? Well, we have differential thermal expansion, or just thermal expansion rather, going on all the way up here as this gets heated. So as this expands, actually this will probably be heat soaked, so it's probably going to, realistically, this whole thing will be uniform temperature. But again, if we're kind of holding it down at this end and measuring at this end and driving from this end, we're not accounting for all the thermal expansion up here in our delta Z. So we need to consider for Z error is thermal expansion. How are we going to handle that? Well, first, two things. I should summarize each of these at the end of the video and include it in notes on the web page. Maybe I'll do that. But as we go through this exercise, we are creating a laundry list of potential issues, of requirements, potential issues that could affect that, and not necessarily solutions. So performance, requirements, and what affects that. I'll just call it effects. And then, at this early stage, when we're still working with the client, we're going to identify areas that we need to investigate. So, before jumping on and fixing this problem, we will try to quantify what that effect is. All right, so we've identified a number of sources of error for the Z, accuracy and resolution. We probably save for another day the contribution of the optical system. Let's stay focused here. You can imagine if there is some kind of wobble that's going on here. So if this is moving or not very rigid, depending on how long that post may be and your guidance, potentially you can have some wobble, which would contribute to XY error there. If you're not, we can address that with multiple parallel shafts, but then that also leads potentially to binding. So especially in a system like this with high temperatures involved, that's a risk. It's nice to have a nice central post, but it's not necessarily going to be as rigid as you might otherwise want. So I'm trying to wrap this up so I can go home to dinner, and everybody else can too. I think we've done enough for today, identifying some of these challenges that we're going to need to look at. Some sources of error for X and Y, but more particularly Z. Some issues with the quality of the part that's produced based on variability in the powder thickness as well as incomplete coverage. So we need to consider that. We think a lot of that will be handled by the spreader, as we've identified. We have the Z-axis as another of our components here. Another subsystem that I think we'll spend some time on in the next few days. And then also we talked earlier on about some of the thermal issues, and that's related to the interface between this movable platen with high repeatability and this base that's heated. And there are a number of ways to address that I think we'll get into. So I'm going to summarize that. The last thing that I would recommend doing, so if you're in this scenario, I wouldn't try and clutter everything quite the way I've done it here. And also when you're done, take a picture of the whiteboard with your cell phone. If you haven't done it before, and if the people in the audience haven't seen it before, they'll just be amazed at how brilliant you are for thinking of doing that. Can't do that because I'm just using my cell phone for recording here. But so let's wrap up here. I can't promise that I'm going to summarize these notes in time, but I'll get this video edited and uploaded for today, day 2. You'll probably see it on October 3rd. And then I'll come back and add some notes and some more takeaways from all of this. But I think we're going to leave it here. And tomorrow we're going to look at, again, we talked about the other part of this product, at least in our notional design, is the palletization. So as it moves from one system to another. And that we're going to deal with defining requirements for that for interchangeability, which will say something about what this interface needs to be so that it will inform the problems that I anticipate with good thermal conductivity across that highly repeatable interface. So let's leave it there for today. Thank you.